Welcome to an intriguing journey into the heart of the atom. Imagine tossing tiny, supercharged cannonballs at a sheet so thin it's only about 1,000 atoms thick. Sounds like science fiction, but this is exactly what Rutherford did in his famous gold foil experiment. But first, what are these tiny cannonballs? They're called alpha particles, which are actually helium nuclei carrying a positive charge twice that of the proton, so plus 2e, and they weigh about 4 atomic mass units. These alpha particles naturally come from certain radioactive materials, and Rutherford cleverly used them as probes to see inside atoms. Now, picture his setup. A source shooting these high-energy alpha particles straight at an ultra-thin gold foil, just a few atoms thick, designed to maximize the chances of particles bouncing off something inside. To catch these scattered particles, Rutherford placed a zinc sulfide fluorescent screen around the foil. Whenever an alpha particle hit this screen, it produced tiny flashes of light, like fireworks marking where and how the particles were deflected. Gold was chosen because it can be hammered into sheets very thin, like the thinnest foil you can imagine, and has a large number of atoms, giving alpha particles plenty of chances to interact. This entire apparatus turned invisible atomic mysteries into tiny, bright sparkles that revealed clues about what atoms really look like inside. Now, here's where things get fascinating. Rutherford's experiment challenged everything scientists thought they knew about atoms. The first surprise was that most alpha particles sailed straight through the gold foil almost as if nothing was there. This told Rutherford something huge: atoms must be mostly empty space. Imagine throwing tennis balls through a bunch of flying paper clips and most of them just zooming through. That's a bit like what happened. But here's the twist. About 1 in every 8,000 alpha particles bounced back sharply, deflecting at angles greater than 90 degrees. According to the prevailing Thomson plum pudding model, where positive charge was spread evenly like raisins in a pudding, such big deflections shouldn't happen. So what caused these big bounces? Rutherford reasoned there had to be a very small, dense center of positive charge inside the atom. Some alpha particles were deflected at intermediate angles too, suggesting this positive charge wasn't spread out but tightly packed into a tiny nucleus, about 10 to the minus 14 meters across, a scale unimaginably smaller than the atom itself. These surprising deflections pointed to an atomic structure very different from the smooth, diffuse models of the time. So, what did Rutherford's experiment teach us about the atom? He proposed a new model where the atom looks a bit like a miniature solar system. At the center sits a tiny nucleus only about 10 to the minus 14 meters in size, containing all the positive charge and almost all the mass. Around this massive nucleus, electrons revolve, attracted by the electric pull between their negative charge and the nucleus's positive charge. Think of planets orbiting the Sun, but on a scale billions of times smaller. The whole atom, by comparison, is roughly 10 to the minus 10 meters in diameter, which means the nucleus occupies an incredibly small fraction of the total atomic volume. This neatly explained why most alpha particles passed through the foil and why some scattered widely. The tiny nucleus was the heavyweight champion, causing those big deflections. But, like a thrilling mystery with more chapters to come, this model couldn't explain how atoms stay stable or why hydrogen emits light only at certain colors, the famous discrete spectral lines. Those puzzles awaited new ideas and led to the birth of quantum mechanics. Now, let's dig a bit deeper and see why alpha particles scatter at different angles. The key idea here is something called the impact parameter, which is the shortest perpendicular distance between the alpha particle's original straight-line path and the nucleus at the center. Imagine sliding a puck on ice past a pebble. How close it passes determines how sharply it turns. Using the laws of conservation of energy and angular momentum, physicists found a formula linking the impact parameter to the scattering angle theta, which is the angle at which the alpha particle deflects. To say it in words, the impact parameter B equals 1 divided by 4 pi epsilon naught multiplied by 2 times z times e squared divided by the product of mass m and velocity squared v squared, then multiplied by cotangent of theta over 2. Here, epsilon naught is the permittivity of free space, z is the atomic number of the nucleus, e is the charge of an electron, m is the mass of the alpha particle, and v is its initial velocity. What this means is the closer the alpha particle's path comes to the nucleus, that is, the smaller b becomes, the larger the scattering angle theta gets, with a head-on collision where b is 0 causing the alpha particle to bounce straight backward at 180 degrees. This relationship elegantly connects the physics of particle motion with measurable deflections. Let's explore what happens in those dramatic head-on collisions where the alpha particle goes straight for the nucleus. At this closest approach, the alpha particle's entire kinetic energy, the energy of motion, gets converted into electrostatic potential energy, which is the energy stored in the electric field pushing the two positively charged bodies apart. We express this energy balance with an equation 1/2 mv squared, that is half the mass times velocity squared, equals 1 over 4 pi epsilon naught multiplied by 2 times ze squared divided by our minimum, where our minimum is the smallest distance between the alpha particle and the nucleus. Rearranging, we find that this closest distance our minimum equals 1 over 4 pi epsilon naught times to ze squared divided by half mv squared. For gold with an atomic number of 79, this minimum distance comes out to about 3.2 times 10 to the minus 14 meters, which gives us an upper limit estimate of the nuclear radius. In other words, the alpha particle can't get any closer without losing all its initial kinetic energy to the repulsive electrical force, giving us a surprisingly precise peak at the size of the nucleus. As groundbreaking as Rutherford's atomic model was, it hit a few speed bumps. According to classical electrodynamics, an accelerating charged particle, like an electron moving in a circle around the nucleus, should continuously emit electromagnetic radiation and thus lose energy. If that were true, electrons would spiral into the nucleus in a blink, and atoms would collapse within about 10 to the minus 11 seconds. But that obviously doesn't happen because atoms are stable. Also, this model couldn't explain why hydrogen atoms emit light only at specific colors, the so-called discrete spectral lines, which are vital clues about atomic structure. These puzzling inconsistencies signaled that new physics was needed. Enter Bohr, who introduced the idea of quantized atomic orbits to fix these problems and lay the groundwork for quantum mechanics. To wrap up, remember these key points. The minimum distance of closest approach, our minimum equals 1 over 4 pi epsilon naught multiplied by 2 ze squared divided by half mv squared, and the impact parameter B equals 1 over 4 pi epsilon naught times 2 ze squared divided by mv squared multiplied by cotangent of half the scattering angle theta. Rutherford's model taught us that the nucleus is roughly 10,000 times smaller than the entire atom but packs almost all its mass and positive charge inside. Large angle deflections of alpha particles provided clear evidence of this tiny, dense nucleus, while electrons orbit around it in the vast empty atomic space. Finally, the classical model's shortcomings regarding atomic stability and spectral lines spurred the development of modern quantum theories. That's it for today's exploration of alpha particle scattering and Rutherford's nuclear model. Physics is a wonderful adventure when you can laugh and learn together. See you next time.